Good morning, Bulldogs. We are looking at chapter 4.3, and what we are exploring today are some behaviors that we can determine about a graph based off of the second derivative. So in the previous lesson, 4.3.1, you learned that the first derivative helps us find intervals where our graph is increasing and decreasing. And it also helps us find local mins and maxes. So that's the increasing, decreasing test and the first derivative test. Today we're going to learn about a concavity test. So I have an opening example that I'd like to look at. So this Bower question says, the figure shows a population for Cyprian honeybees raised in an apiary. How does the rate of the population increase change over time? So we've got time on our x-axis, number of bees on our y-axis. So obviously the population itself is increasing, but this question is really saying, how does the rate of the population increase over time change? And the rate would really be how quickly the number of bees over time is changing, which is your slope of your tangent line. So if you look at the slope of your tangent lines at the start of this graph, 3 weeks in, 6 weeks in, the rate of change of the number of bees, the population rate, is increasing. It's getting steeper in terms of the slope of the tangent line. And then right around here it starts to change and my tangent lines start to flatten out a little bit. You know, if you wanted to, you could draw a few tangent lines in here. They're getting steeper, they're getting steeper, they're getting steeper. Maybe right around in there you hit the steepest and then they start to flatten out again. So we can see that by the time you get to 18 weeks, our population rate of change is flattening out. So the population of honeybees is not increasing as fast. So the question really is, when is the rate the highest? So just looking at the slope of the tangent line, it looks like the rate is the highest right around here. And what I'd like for you to note is the curvature of the graph. So everywhere up until that point, since our tangent lines are all below the graph, but the tangent lines are getting steeper, 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 this interval is actually what we call concave up. And then after that point, all of our tangent lines are actually above the curve itself, and this is concave down. And in that concave up interval, our rates of change are increasing. And in that concave down interval, our rates of change are decreasing or eventually flattening out. And this magical point where we switch from concave up to concave down, we call this an inflection point. And what we're going to do today is we're going to identify inflection points and we're going to classify intervals as either concave up or concave down. So let's jump to the next page in our notes packet. I am now on page 9 of your notes packet here. And up at the top we have a definition. If a graph of f lies above all the tangents on an interval, then it is called concave up. So the graph is above the tangent lines, is concave up, and what I always say is it is concave up like a cup. So almost imagine a cup that would hold water. So that type of curvature is what we call concave up. And when we have a graph that sits below all of the tangent lines, that is concave down. Or I like to say concave down like a frown. And so that type of curvature where if you were to drop water on it, the water would just spill up the side, that is considered concave down. Realize that I drew a complete curve, but it could also just be a piece of the curve. So this is concave up, this is concave down. Our concavity test says that if our second derivative of our graph is greater than 0, then the graph is concave up. If the second derivative of the graph is less than 0, it is concave down. And if we find a point called an inflection point, where the graph is continuous everywhere, but our curve changes from concave up to concave down or concave down to concave up, then we know we have an inflection point there. There must be a sign change in your concavity. All right, so let's take a look at a couple of examples. So example number 1. Find the points of inflection and discuss the concavity of the graph. So we have to find our second derivative here. So let's start with the first derivative. So that would be 6x squared minus 6x minus 12. And then let's find our second derivative. So 12x minus 6. We're going to set that equal to 0 and solve. Oh, the reason why I'm setting it equal to 0 is since I want to look for when the second derivative is greater than 0 and less than 0, just like with our increasing decreasing test, we have to start by finding where it is 0. And then we're going to graph a sign diagram and test our values in our second derivative around those critical points. So what we're finding here, we found our second derivative. We set it equal to 0. We are finding that we have a critical point at 1/2. Is it an inflection point? We don't quite know yet. So I am going to graph a number line, and I'm going to plot my critical values that I found for my second derivative on that number line. I'm going to choose number to the left of 1/2 and to the right of 1/2, and I'm substituting that into the second derivative right here. So a nice number to work with less than 1/2 would be 0. So let's substitute 0 in here. 12 times 0 is 0, minus 6 is negative. And I am substituting into f double prime up here. So this whole interval would be negative. A number greater than 1/2 would be 1. 12 times 1 is 12, minus 6 is positive. So we've got a couple things happening. First of all, I know I want to identify inflection points. And if I have a change from concave up to concave down, I have an inflection point. Well, let's identify when it's concave up and concave down. So when my second derivative is greater than 0, it is concave up. That means this whole interval in here, where my second derivative is greater than 0, that is concave up. And everywhere where my second derivative is less than 0, it is concave down. So we're going to first identify those intervals. So it is concave up from 1/2 to infinity. It is concave down from negative infinity out to 1/2. I'm not including those endpoints because at 1/2, my second derivative is 0. It's neither positive nor negative. Okay, so we do have a sign change, a concavity change, which means there is an inflection point. So you can call that an inflection point. You could call that a point of inflection, whatever you want to refer to it as. And our x-coordinate of that point of inflection is 1/2. So I do need to substitute 1/2 back into this function to find my y-coordinate. We always go back to the original function to find a true y-coordinate. So I'm going to squeeze this on in down here. So f of 1/2. So we would have 2 times 1/2 cubed would be 1/8. Minus 3 times 1/2 squared would be 1/4. 12 times 1/2 is minus 6 plus 5. So let's clean this up a little bit more. So that simplifies to 1/4 minus 3/4. Negative 6 plus 5 is minus 1. If you want to find a common denominator, great. If you want to go mixed fractions, that's okay too. I'll go ahead and find a common denominator. So 1/4 minus 3/4 minus 4/4. So 1 minus 3 is negative 2. Minus 4 is negative 6/4, which is negative 3/2. So my inflection point is happening at negative 3/2. And just so you know where we're going with this is we're eventually going to be sketching all of these curves. So the concavity helps us determine what the curvature of this would be a concave down, this would be a concave up. We have a point of inflection at 1/2 negative 3/2. Okay, let's take a look at one more example. So example number 2. Now you can expand this out if you want, or you can use your chain rule. I'm going to just go ahead and use my chain rule. So my first derivative would be my 2 comes to the front, my power drops down to a 1, times the derivative of the inside part, which is 2x, So if I clean that up a little bit, that's going to be 4x times x squared minus 1. And now I need to find my second derivative, but I'm thinking I'd rather, instead of using the product rule, I'm just going to distribute this out. So I'm just going to rewrite this as 4x cubed minus 4x, and now I'll find my second derivative. So that is 12x squared minus 4. Let's set that second derivative equal to 0. And solve to find my critical points, which I will plot on my number line. So I'm going to slide my 4 over to the other side, divide by 12, so 4 over 12 is 1/3. And I'm going to take the square root of both sides, which gives me plus or minus the square root of 1/3. I'm fine with you leaving it like that. If you're an IB, they're okay with that. If you want to reduce that, that is the square root of 1, which is 1, over the square root of 3. And if you rationalize that, that is multiply top and bottom by square root of 3, you get square root of 3 over 3. Okay, so we're going to now plot this on a number line. So I'm going to head over here. And I've got 2 points to plot. I don't care what version of this you plot, but I'm actually going to go with the one that is more comfortable to me in terms of where it falls on the number line. So I'm going to plot negative square root of 1/3 and positive square root of 1/3. And we're going to substitute numbers around those x values into my second derivative. So my second derivative is this function right here. So I'm going to start all the way on the right. I know a number bigger than square root of 1/3 would be 1. So 12 times 1 squared minus 4 is positive. Let's substitute 0 in. 0 minus 4 is negative. Substitute a negative 1 in. Negative 1 squared times 12 is positive. 12 minus 4 is positive. So let's identify our intervals. So this is going to be concave up everywhere that my second derivative is positive. So from negative infinity to, now you can put negative square root of 1/3, but knowing the AP textbook, they're probably going to use that rationalized version. So they'll probably put negative square root of 3 over 3. And then it's also concave up from square root of 1/3, which is the same as square root of 3 over 3, out to infinity. And this function is concave down in between the two. So that would be from negative square root of 3 over 3 to positive square root of 3 over 3. Do we have any inflection points? Yes, we do. We have a concavity change at negative square root of 1/3 and positive square root of 1/3. So for my inflection points, we're going to list them. I'm going to go ahead and list them with the most reduced version. So one of them is at negative square root of 3 over 3. And the other one is at positive square root of 3 over 3. So I just need to find a little bit of space on here to plug those in. So I'm going to come down here. So f of negative square root of 3 over 3. Now I'm going to plug into this function here. And I'm actually thinking it would be easier if I use the negative square root of 1/3. Just assuming that when I square that, that radical is going to go away. That's going to get a lot cleaner. So you can substitute whichever one you want. You can certainly use a calculator if you want. So I'm going to substitute a negative square root of 1/3 in here, squared minus 1 squared. So negative square root of 1/3 squared is 1/3. Minus 1 is negative 2/3. Squared is positive 4/9. So my y-coordinate is 4/9. And if I substitute a positive square root of 3 over 3 in, or that's the same as positive square root of 1/3, we're going to get square root of 1/3, quantity squared minus 1 squared. Isn't that going to give me the same exact number? I'm going to get 4/9 again. So now we have our concave up intervals, our concave down intervals, our inflection points, or our points of inflection. All right, there is one last thing to consider in this section, and this is something called the second derivative test. And it is actually purely optional for you to use. The second derivative test has nothing to do with concavity and inflection points. It's actually an alternative option to identifying mins and maxes. So what it says is, remember when we identified a local min and a max yesterday in our previous lesson, we looked for where the first derivative was equal to 0, and we looked for where we had a sign change, where our graph changed from increasing to decreasing would be a max, and decreasing to increasing would be a minimum. Well, what this is saying is, if you know your first derivative is equal to 0, so you know the slope is 0, and you also know your second derivative is greater than 0. If your second derivative is greater than 0, this is actually concave up. And if you know that your slope of your tangent line is 0, let's think about what a local minimum would look like. That is a concave up interval. And at this point right here, at letter C, my tangent line would have a slope of 0. So that would meet both of these criteria. So why would I choose to identify a local minimum using this technique instead of the first derivative test? On the first derivative test, you still have to find where your derivative is 0, but then you have to plot it on a number line and test your intervals. So really, this is just an alternative. If you don't feel like plotting the first derivative number line, that's fine. This is a second option for you, especially if you're already finding your concavity. For the second scenario here, if your slope is 0, but the second derivative is less than 0, which means it is concave down. Well, let's think about what a concave down interval looks like with a slope of 0. So if that were letter C right here, we know we have a tangent line with a slope of 0, and we know the second derivative is less than 0 because this is concave down. Of course, we have a local min. I'm sorry, a local max, excuse me. And again, this is an alternative to graphing your first derivative critical points on a number line and testing your signs. I barely use the second derivative test because we're always finding where the first derivative indicates increasing, decreasing intervals. And if you have to already find that, then you really don't need to go further. If you know when it's increasing, decreasing, you already know where your local mins and maxes are. Okay, that's the end of our concavity lesson. Thank you so much for listening today.